If we look closer into the design of a Snoop-based cache-coherent architecture, we'll see that it's not as simple as what we saw before. In fact, in order to get sort of full access to the cache from the CPU, we typically duplicate the tags, which means that the address tags and the state bits here gets duplicated in a separate hardware mechanism so that the CPU can access the address tag at the same time as the bus snoop, when you snoop on the bus for looking up in the cache memory. And only when you have a hit in the snoop tag, then you may possibly need to do some action on the data store of the cache itself. So most bus transactions will actually miss in the bus snooping mechanism. So it's sort of wasteful to occupy the cache mechanism by snooping when you don't need it, so that the CPU can get access. We call the data cache tags the access tag, which also tells the processor what permission it can do. We call the other one, we call the snoop tags, which is the obligation state. It tells the system what this processor or this core has promised to do with respect to cache coherence towards the other processors. So let's look at the previous sort of upgrade transaction in more detail here. So this picture shows two cores. We have one here, and we have the other one in blue to the right? So these are two cores. We will only see the one CPU here because we will only look at one CPU as being the sort of the initiator of transactions here. The other CPU is not visible, but we will see the snoop, at least the snoop mechanism here. Okay, let's see what happens here. So the cache line that we are interested in here in this example is in state shared, which means that the cache contents is equal in the two caches. We have state shared here and in the obligation state. Okay. There is a queue to the cache from the snooping mechanism, and here lies some sort of requests from earlier transactions that need to be fulfilled eventually. So now we have the store being made at the CPU that resulted in this bus invalidation message as we saw earlier on. This will be snooped by both cores here. So our own core will snoop it, and it will be seen as an acknowledgement, because we now then have acknowledgement that this store has been globally visible for all other cores. This is an important thing. The globally visible, this means that you can't really turn away. This is the point of no return. You can't go away from this this store any longer. This also means that we can go from shared to modified state in the obligation state. This is what we have promised to do. As soon as the other core sort of snoops here, it will also change its obligation state to invalid. And it will put this invalidation pill in the queue behind the earlier transactions, and eventually it will be processed. When the cache, sort of CPU cache mechanism sees the acknowledgement, we change from shared to modified also in the local cache. And now the store can be carried out, and you can modify this cache line here, right? So this cache line can now be modified. It's okay that the other cores can continue and read from the old data, because it's the invalidation here on the bus that sort of orders all memory operations. So there cannot be another memory operation to this block until all the cache, at least not from this processor here to the right, until the invalidation has been processed here. You can't do a store, for instance, because the store will have to go to the bus, and then the acknowledgement will come after the invalidation here, and then you have to process the invalidation before you can do the store. So all transactions to this particular cache lines are ordered. If after the invalidation we have a read from another thread, we have to do a cache-to-cache transfer, and let's see how that is carried out here. So on a superficial scale, this is what happens. So we have, this is from the CPU side, this is the core that had the block, the cache line in the shared state earlier, but now it's been invalidated, and you do a CPU read caused by the load. You have to transfer a bus read to share on the bus, and then go to the shared state. So the load leads to, and we see that we get a cache miss. We have to send the bus read to share, and then let's see what happens on the other cache line. Here the cache line is in state modified, right? You'll see the bus read to share. You have to supply the data on the bus and then transfer to the own state. You see the bus read to share is in a modified state. We go to the own state. Now we're done. Let's see how that looks like in more, and supply the data, of course, in more detail with the same kind of detail we had before. So the border between the two cores are here. So now we switch the side. The CPU that performs the load is the one that has it in the invalid state, and the one that will reply to it is the one that had it in modified state before. So the initial state here is that we have it in modified state on the right hand side, and the invalid state on the left hand side. So we do the load. That will lead to a bus read to share transaction on the bus. This will be snooped by both cores. Our own processor core, will see the my RTS, which first of all will make the modification that the obligation state go from invalid to shared, but we can't change the cache from invalid to shared until we have the data, so we have to wait for the data. So until the data comes back, this my RTS pill sits here and just waits. And basically the processor just sits here and waits. If this is a cache that can support multiple outstanding loads and stores, this is fine. But for now, it will just sit and wait. Okay, the other core will snoop the transaction. It will change the obligation state to own state. It will put the pill in the queue here, and eventually this cache will eat this pill and change to own state, and then reply with the data over the bus, of course. But the result is that when the data comes back, the my RTS pill will go back, and you can continue with the data. And now the end result is that the cache is in shared state here, own state here, and the obligation state and the permission state are all the same. Let's have a look at the different kind of cache-to-cache transfer. So in this case, we have the cache line in the own state. So if we see someone else who wants to read the data, bus read to share, we have to supply the data. And that's a cache-to-cache transfer. So we see the bus read to share, and we have to supply the data.